Okay, so we're going to start talking about quasi-linear equations. Quasi-linear equations are not linear, but they are nonlinear in a very sort of structured way that lets us really apply the method of characteristics. They come up a lot. We're going to derive some PDEs today that will turn out in some cases to be quasi-linear. But they also have some interesting features that we will see as we go throughout this week. Okay. So the general quasi-linear first order equation, so we're going to have the PDE, a of x, y, u, times the x derivative of u, plus b of x, y, u, times the y derivative of u is equal to some function x, y, u. So here the functions a, b, and c, these are all given. And we assume that this is on some domain omega, and we assume that we know that u is equal to some given function on a curve gamma through the domain. So for example, if this is like xy, this is omega, and then maybe this is gamma. So we know what u is on that curve there, and from that information we want to try to figure out, and from that information and the PDE, we want to try to figure out what the difference is, we want to try to figure out what the solution is on all of omega. Okay, so what is the difference between a linear and quasi-linear equation? Well, just look at what's going on here. So we're allowed to, the things that we're multiplying the x and y derivative by, those involve u. So the functions a and b involve, or at least could involve, the unknown function u. And before we didn't have that. When we're dealing with linear equations, the a and b functions were only functions of x and y. Okay, so how does this make a difference? Well, the first way is that if I look at the characteristic equations, x dot is going to be a of x, y, z. Okay, remember z is equal to u. That's going to be x naught. Y is b of x, y, z. And this is going to be y naught. So this point here is chosen to be on the curve gamma. And then finally, let me just remind you, as always, z of s. I'm already using this up for x and y. This is equal to u of x of s, y of s, and if I do the chain rule, z dot of s is going to be x dot times the x derivative of u plus y dot times the y derivative of u. Okay, well, x dot is a and y dot is b, so this is a times the x derivative of u plus b times the y derivative of u. And if I look up at the PDE, that's just going to be equal to c. So this is going to be equal to c. So c dot is equal to c of x, y, z. And z of 0 is just going to be u of x naught, y naught. Okay, so this is still a system of first order differential equations. But the important thing now is that x dot and y dot can depend on z. So in other words, the characteristics themselves are going to depend on the solution. And that's not something that we've seen so far. So far we've been able to solve the x and y equation without talking about the z equation. And we know that if there's sort of this uniqueness theorem with ordinary differential equations that would sort of indicate that the characteristics are not going to intersect. However, if we're now including this z in this, the x and y characteristics can intersect because they now depend on z rather than just depending on x and y. And that's going to be a big deal in the analysis of these PDEs. Okay, that's it for this video. In upcoming videos, we will derive some PDEs and then look at analyzing some of these quasi-linear PDEs using the method of characteristics.